right off the corner of the mattress that you stole from your roommate like you bowler. We ain't never getting older.
Right, okay. Enough of that. So, hello and welcome to this revision lesson on the physics units we've covered so far. Basically, I'm going to go through the ideas that we've covered using a series of apps. Okay, so these are web apps that you can get from this website here. Okay, so it's called PHET, and it's produced by the University of Colorado, which is in Boulder, hence the song by the Chainsmokers and the dodgy dancing once again, Dan. So, just in case you don't know where this is, where I'm talking about, there's a University of Colorado in Boulder, and we are over here. So that's the University of Colorado in the States. Other side of the Rockies by the looks of it. Maybe I've got that wrong, but that's the West Coast, that's the East Coast, that is the University of Colorado Boulder. Okay, so on to the website apps of choice. So what we're going to look at first is the first topic we looked at was speed, distance, and time. Right, so here's an app I downloaded from that uh, website. Okay, so we have a gentleman, and maybe he's gone for his hour walk. We've got his house, and we've got where he's gone for a walk. Okay, and what we're going to just illustrate is this concept of speed. So if I click play, you can see that he is moving with a velocity of 1 meter per second. So that's 1 meter per second on his way back home. Okay, but what does that actually mean? Right, so what does speed mean? Right, so if we go to 1 second, we can see that this gentleman in the fancy suit has travelled 1 meter in 1 second, so his velocity is 1 meter per second. So speed is how far you travel and how long it's taken you to get there. All right, so if we clear this, okay, don't worry about what I'm putting in here. You don't need to learn it. All right, so okay, that is enough of that. Let's have a look at the playback. So this we're going to go for the same time period. Okay, the same period of time, and let's see how far he travels. So, oh, nearly. This time, in 1 second, he has travelled 2 meters. Okay, slightly over because I'm slightly over 1 second. So his velocity is 2 meters per second. So that's speed in a nutshell. Right, that is speed or velocity if we give it its vector form. Right. So, for example, velocity is a vector because if I now we say, oh, I'll just clear that. Right. So now you can see it's a vector because the velocity is minus 1 meters per second, which means he's going the other way. Maybe on his walk, he dropped his mobile and he's gone back for it, right? So velocity is the vector, speed is the scalar, right? So his speed is 1, right? It's 1 meter per second, right? But this time he's going in the opposite direction. Okay, so that is speed, distance, time. Right, we've got some charts. Oh, he's not moving. Let's give him a velocity of 1. Right. So as you can see, he is accelerating, or his velocity is constant, so he's got no acceleration. Velocity is constant. His position, the distance he's travelled, or the displacement, is increasing at a nice steady rate. So his position is increasing in a nice steady rate. Okay. Right, so that is speed, distance. Pause me, lovely. That is speed, distance, time, and that is these are examples of the moving man's speed. This is distance time graph, and this is a velocity time graph. Okay, so distance time graph, and it's a velocity time graph. It had that initial blip because he accelerated from nothing. Yeah, had no speed, no velocity, and then accelerated really quickly to a constant velocity. Okay, right, lovely. So that is speed, distance, time. We're now going to move on to the next section, which is forces. All right, so forces, I've already set up this scenario here. This is once again FET. And what we've got is we've got a tug of war, we've got our blue team, and we've got our red team. And if I click go, we've got a little meter that tells us how quick we're going. We've got the left force, 50 newtons, and the right force. If you click go, we've got this situation here. We say the forces are balanced. Okay, so this is Newton's first law. Newton says stuff ain't gonna move if the forces acting on it are balanced. Okay, so Newton's first law, that's numero uno, says that objects will remain at rest, that means stationary, or at a constant velocity if the forces acting on it are balanced. Okay, so now let's switch it up a little bit. Before I do that, if you notice, the sum of forces, what we call the resultant force, is 0. So let's go get this big boy here, and let's add him to, or her, because you don't know if it's a lady or a bloke, do you? Right? No discernible features. So as you can see now, the left force is greater than the right force. So the resultant force is 100 newtons to the left. I just want you to contemplate, to think for a second or two, what might happen. Okay, let's think about what is going to happen. Okay, if you were thinking, well, it's going to move to the left, bang on. Right, in fact, what do we notice about the speed? It keeps on increasing. Okay, so in fact, it's the tug of war is accelerating to the left. Okay, we're getting into Newton's second law territory here. So an object, basically, if you apply an unbalanced force, an object accelerates, right? So if we go into here, we've got our skateboard, we've got our pusher, and what we're going to do is we're going to apply a force of we're going to apply a constant force of 100 newtons, right? If you notice, the speed in this bar up here continues to increase, right? So this is Newton's second law, going up and up and up and up, right? Because it's gone too quick, right? So when he applied a force, the object, in this case a wooden crate, continue to accelerate. Okay, what we also notice here is this is another example of Newton's first law. An object will remain at rest or at constant velocity unless an external, another force acts on it. So this will keep moving at 40 meters per second unless I try to slow it down. Okay, good. So now I'm pushing the opposite direction. I'm going to cause it to decelerate. Okay, down to nothing. Oh, so very nearly nothing. Okay, right. So just move my face a second. Will it allow me to? All right. So let's see if we can stop it completely. All right. Okay, so let's do the same process, but this time let's add some more mass, right? Let's add some more mass to this object, right? So I've added a lot of mass there now. I've added the bin, the lady, and the gentleman. So I'm going to try and apply that same force, and it should take longer to accelerate. So force was about 100 newtons. It was slightly over, if I remember. All right. So you see, try and keep that force constant. It's taking a longer time for that mass to accelerate up to the top speed of 40 meters per second. See, it's a lot slower than it was before. And you can go back in this video and time it. I'll probably do that when I edit it afterwards. Okay, so it's going to take a while. It's not accelerating as quickly, and that's basically Newton's second law. Newton's second law says that how quickly something accelerates depends on the force, right, and the force applied and the mass of that object. Okay, so it's taken ages, but you get the idea, right? If I release that, the object will continue to move because there's no external forces acting on it. Of course, in reality, we have this thing called friction, which acts to the left, that's going to slow this object down. Okay? Right, so just to demonstrate in reality, we have lots of friction. Right. We could apply, oh, too much friction. Right. We've got this friction. It is moving, it's accelerating, right? I'm applying 247 newtons, as you can see at the bottom. Right, we'll get up to 40, and this time, watch what happens to the speed. Yes, okay, it's decelerating, it's slowing down because we've got unbalanced forces. Right, so Newton's first law and Newton's second law. So Newton's first law is unbalanced forces, so it will change speed, it will accelerate, in this case decelerate, right? And Newton's second law, the rate at which how much it decelerates it was equal to how big that force was. Okay, all right. Let's just get this going again. So what we notice here is Newton's third law. Okay, for every force, there's an equal and opposite force. So we notice this friction force is stopping this crate from moving at the moment, and the force from the test dummy, the orange guy, is equal and in the opposite direction. So this is Newton's third law: equal and opposite forces. Right? Eventually, we get enough force to have a resultant force causing the acceleration. Okay, right. Try and speed that be a bit quicker. That's a little bit, oh, cool. So this really helps us to see what's going on here. So balance forces. Then we have a applied force of 132 newtons. This will be really good for Newton's second law. Okay, the harder you push, the quicker it should accelerate. So I'm going to apply even more force. Notice the acceleration has just jumped up, right? The acceleration has jumped up. Even more force accelerates even more. Even more force accelerates even more. It's going to fall off. Ah! Right? And notice now we've got a constant deceleration. Right? We've got a constant deceleration, which is decreasing the speed. I make the... Oh, it doesn't change that. Thought it might do. Excellent. So they are Newton's laws in summary. They're Newton's laws. So we've got the first law, which is basically stuff stays still or moves at a constant velocity if it's got balanced forces acting on it. So that was R1 there. Constant velocity because it's got balanced forces. Okay. Force forward, the same as the drag coming backwards. Right. Newton's second, probably this is the best scenario. Let's get it again. Right. So basically, how much it accelerates is dependent on the resultant force, the sum of forces. Okay, so if I increase that, so it accelerates more, as it says in the acceleration bar. Right. And also, I'll let that go down. Lots of friction, let's slow it right down. If I increase the mass, it's going to take a greater force to accelerate it by the same amount. So you see, I'm going to need a bigger force than before. Look, it's not even moving. So I need a massive force. Oh, I can't even get it accelerated. Okay, cut that down a bit. All right. See, I need a massive force to get any sort of acceleration. This is Newton's second law once again. What we're looking at now is the force gravity. Okay, so we looked at forces and how they cause objects to accelerate. So we have the Earth and the Sun not to scale, Earth and the Sun not to scale, but the masses are right. Okay, so a lot of us said that gravity doesn't exist in space. That is not correct. Okay, gravity does exist in space. Right. So here we see the Earth accelerating around the Sun. Okay, and this is a tricky bit really, because look, the velocity isn't changing, the speed isn't changing, but we say the Earth is accelerating because remember, forces cause acceleration. What the gravity force is causing, it's causing the Earth to change its natural direction. The Earth would normally, without any gravity, would just fly off, as demonstrated here. I've just turned the gravity off. Without gravity, the Earth would just fly off into space, and we wouldn't have the sun. You know, we wouldn't have summer, we wouldn't have plants, right? So this time, we're just going to demonstrate. So this hopefully demonstrates to us that gravity does exist in space, right? It's what keeps the Earth in orbit around the sun. It's what keeps the moon in orbit around the Earth. Okay. Now I'm just going to increase the mass of the Earth. Let's see what happens there. All right. So we've got this orbit. Let's make the mass even bigger. What do we notice about those orbits? Let's make the sun even bigger. Ah, here we go. So it's causing the Earth to accelerate, increasing the mass, right, is increasing the size of gravity, right? It's made this really weird orbit. This, what we call an ellipse. It's like a squashed circle. Okay, so gravity exists in space, right? And if we have more mass, the bigger the object, the bigger the force of gravity. Okay, so the amount of gravity depends on how massive, how big the objects are. All right. Oh, we're going to crash into the sun. Ah, yes. Oh no. Right. So let's go the other way. Right. Let's go the other way. Alright, this time we're gonna, let's get this going. Alright, we're gonna make the mass less. So that should be less gravity, so less acceleration towards the sun. Indeed, that's what we're getting here. Right, the gravity's really weak, so the Earth is sort of doing its own thing here. Okay? So two things that affect, or the main thing that affects the strength of gravity is the mass. Okay, the other thing that affects the strength of gravity is the distance. Okay, we can't really float on the ground because the strength of gravity is so big, right? So if I bring the Earth or this planet really close to the sun, do you notice those forces of gravity get really big? Okay, all right. So that's gravity. Okay, that's gravity. So gravity exists everywhere in space. It just gets weaker and weaker and weaker the further objects are away and the less their mass. So if I increase the mass, the bigger the force of gravity. If I decrease the mass, the smaller those forces of gravity. Yeah? Increase the distance, the smaller the force of gravity. Last one.
If I die before I wake, at least in heaven I can skate.
There we go. So last one. Right. Okay. So last one. Here we are. So this, instead of talking about forces now, so we're talking about speed and velocity and acceleration. We talked about forces. We moved on to the force of gravity and the factors of things that affect it. So now I'm going to talk about energy and energy changes. So I have my skater girl, all right? And when the skater girl's on the ground, she ain't moving, right? She is not moving. As I lift her up, she gains gravitational potential energy. All right, she gains gravitational potential energy. Now she drops into this half pipe. Watch what happens. All right, I'm gonna slow it down. All right, back up. Okay, so as she goes down, that gravitational potential gets converted into kinetic energy. All right, and at the bottom, it's maximal kinetic energy. Right, i.e., nearly all that gravitational potential has been converted into kinetic. If she's perfectly at the bottom, then it all has. All right, mess this up. Down. Oh, I'm just going to drop her in again. All right, and then on her way back up, that kinetic energy gets converted back into potential. So it's like this seesaw motion we've got, like this swinging effect. Potential into kinetic, kinetic back into potential, potential into kinetic, kinetic back into potential. And you notice where a speed is at the greatest, her velocity, the amount of kinetic energy she's got is at the bottom. Yeah, we see that? Of course, in reality, once again, we have something that's going to slow you down. Okay, we call that friction. So in reality, the skater has to keep pedaling. All right, get slower and slower and slower and slower. All right, so more and more of that energy gets converted into heat because of friction, and you can know that friction produces heat when you get your hands and rub them together. It's hot, all right. So as you can see now, all that potential and kinetic energy has been converted or changed into thermal, and she's not moving. Right, let's finish with a bit of fun. Right, let's just set up a loopity loop. All right, let's see if we can get it to do a loop the loop. Let's see if we can pull this off. And also, we'll finish with a kicker. There we go. So, I wonder if that drop in's high enough. Let's make that a bit more rounded. Okay, so the learning's basically over. This is a bit of fun. Alright, let's make it a little bit larger too. Let's make this. Alright, here we go. No. Let's make it realistic. Let's make it so she can fall off. Just dropping in. Oh, yes! Beautiful. So let's have a look at those energy changes. So interkinetic, losing some as thermal, but still has enough energy to do a nice little jump at the bottom. One more time in slow motion. Gravitation potential into kinetic, losing a bit as bit of it's converted into heat, but she has enough gravitational potential to get off that last kicker. Nice bit of air, makes the landing. Okay, so that is the physics. Physics by a couple of apps. Okay, I have missed out power and work, but we'll look at those in a future revision lesson when we move on to the equations, to the maths. So just to summarise, hopefully this video has given you a good understanding of velocity, of forces and Newton's laws, and then gravity, and then finally energy changes, going from gravitational potential to kinetic, as well as heat energy getting involved in friction. Okay, thank you very much for watching this video. Take care.